Hello, Algebra 2 CP students. Hopefully you're having a great day so far. You may notice it's a little dark around me. It's because I'm recording this video at about 8:30 p.m., but it's not going to stop us from doing some math. And speaking of which, we have a lot of math to get through today, so I don't want to waste too much time with the introduction. But let me just quickly say that what I'd like to do today is talk about complex number operations. First, I'm going to define a complex number for you, and then I'm going to teach you how to add, subtract, multiply, and divide complex numbers today. And that, plus the radical stuff that we talked about, add, subtract, multiply, divide, radicals, makes up the entirety of this unit. The rest of the time spent in this unit will be a lot of practice time, which I think for topics like these where you're just doing operations and simplifying, I think that's really the best way to learn is to just try a bunch of practice problems on your own. All right? So, I wanted to make sure we had plenty of time for that in this distance learning structure, and we absolutely will after we get through this today. All right? So let's get into it. A complex number is actually something entirely new concept. To define it, it is a single value that contains both a real and an imaginary component. And of course, that imaginary component means that there are going to be i's included as well. So it's a value that contains both a real and imaginary component. All right. Complex numbers are expressed in the general form of a plus bi, where a is your real component and bi is your imaginary component. So it's like this value is actually kind of straddling the line between real numbers and i's, right? It has some portions of real numbers in it, and it also has some portions of imaginary numbers in it. And one thing that's kind of weird to get used to, and something that you'll have to kind of get to grips with when complex numbers, is the fact that something like this, 2 plus 3i, is actually a singular complex number. This is a singular value. It's not two separate things, as it seems to be. But it's a singular value that has a value of 2 from its real component and a value of 3 from its imaginary component, represented as 3i. All right? So it's, again, a number that sort of straddles the line in both areas. Now, why are these important? Well, these are going to come up a lot later when we're dealing with solving quadratics in our next unit, but also because we can perform all sorts of operations with complex numbers, and sometimes we actually get real numbers as results. All right, so let's dive into some operations with these complex numbers, and let's start by adding and subtracting. All right. And adding and subtracting complex numbers, in my opinion, is actually one of the easier things that we do. Suppose that I have, for example, I have 2 plus 3i, my same value that I used to start, plus negative 6 plus 8i. Okay? Well, in order to add and subtract these together, think as if these were just x's instead of i's. If I had 2 plus 3x plus negative 6 plus 8x, what would I do? Well, I would combine all the like terms. We would do 3x plus 8x and 2 minus 6, right? Well, it's exactly the same when we're dealing with i's. We would just say, let's combine those real components. The 2 and the negative 6 is going to make negative 4, 2 minus 6. And then 3i and 8i is going to make a total of 11i. And so, writing our complex number in this form of a plus bi, all the non-I stuff first and all the I stuff second, we would say that our final answer is this complex number of negative 4 plus 11i, which just came from 2 minus 6 to get negative 4, the real components, 3i plus 8i to get 11i, which are the imaginary components. All right? So adding and subtracting works pretty much like combining like terms. Right? I always think of this as, in fact, combining like terms, where any real components are combined together and any imaginary components are combined together. The thing we have to be wary of is when we have a minus sign that may distribute to everything. So for this as an example, we have negative 8 minus 3i minus 4 minus I. All right, consider something like that, right? Well, we have to remember that this negative sign, just like if it were an equation, would apply to both this 4 and this minus I right here. So I would combine these terms by saying it's negative 8 minus 4. Negative 8 minus 4 is going to be negative 12. And then negative 3i minus negative I minus negative is going to be a positive. So we have negative 3i plus I is negative 2i. We would say that this is the number negative 12 minus 2i. All right, hopefully that makes sense. Just combining like terms with just a little bit of a negative distribution there. After that, let's do one more adding and subtracting just with radicals instead. Let's throw in some square roots. Doesn't change anything really. If I had the square root of 3 plus 4i, don't be scared, we can handle it, minus 5 rad 3 minus 6i. All right, how would I handle something like that? Well, just because these real components are radicals doesn't mean that the rules suddenly change and everything gets flipped upside down. I would just say, well, here we have 1 square root of 3 minus 5 square roots of 3 is equal to how many square roots of 3? 1 minus 5 is going to be negative 4 of them, negative 4 square roots of 3. And then I have 4i minus negative, so plus 6i is going to be plus 10i. And so my complex number that this would be equal to would be negative 4 rad 3 plus 10i. Okay? And again, what's kind of weird in the realm of complex numbers is that this is a singular value. It's a value that has this much from its real component and this much from its imaginary component. Okay? But again, almost treated exactly as if they were x's. Right? Cool. That's adding and subtracting in a nutshell. And like I said, later this week, we're going to do a whole bunch of practice problems on that. But let's talk about, for the sake of time, multiplying. Okay? Multiplication problem, a standard one, might look like this. We have negative 2 plus 3i times 4 plus 5i. All right, consider something like that. Well, once again, think about if this were negative 2 plus 3x times 4 plus 5x, and I were multiplying those two binomials together. What would I do with those two binomials? Well, hopefully you're thinking to yourself, ooh, I would distribute. And you're absolutely right. I would do negative 2 times 4, negative 2 times 5i, 3i times 4, 3i times 5i, right? You may remember that as sort of an acronym of first, outer, inner, last, which stands for FOIL. I don't like to use the word FOIL because it's not a real math word. It's just an acronym that helps you remember that the steps are first, outer, inner, last. It's really referred to as the distributive property. So I hate that I even said that aluminum-related word on video because I'm sure someone's going to take that out of context and post it everywhere that I actually said it. But we're going to say that this is the distributive property. But you're absolutely right that I would do first, outer, inner, last. Okay, the distributive property. Later on, I'll get into my big rant as to why I don't like that aluminum-related acronym. But for now, let's call it the distributive property. Okay, so in order to do this, I would say, let's do it. Negative 2 times 4 is going to be negative 8. That's our first. Negative 2 times 5i is going to be negative 10i. Inner, 3i times 4 is going to be plus 12i. And last, 3i times 5i is going to be careful, plus 15i squared, because I times I would make I squared. Okay? So just like how adding and subtracting is combining like terms, we would say that multiplying is like the distributive property, where we're just doing our first, outer, inner, last. Now we can clean up this expression a whole bunch by combining like terms and dealing with this 15i squared. What do we know that I squared is equal to? Well, according to my chart, I squared would be the square root of negative 1 squared. So it would be negative 1, right? We know that this fact of I squared is negative 1. So because of that fact, we can say, well, 15 times I squared is the same as 15 times negative 1, which is just negative 15, right? So all in one step here, I'm going to combine the like terms in the middle. Negative 10i plus 12i is going to make positive 2i. And I'm going to say that 15i squared is the same as 15 times negative 1, or minus 15. Last but not least, I'm just going to combine those like terms. We have negative 8 minus 15 is negative 23 plus 2i. And that is now my complex number written in this a plus bi form. Notice the I always comes second, so we're done. Okay? You're going to see actually why that's important when we get to division, and that's why I always emphasize writing in this form, because if you don't and you move into division, things can get kind of mixed up. All right? Let's take a look at a couple more examples of multiplication before we go into division. How about if I have negative 8 plus 4i times 1/2. Don't be scared by that. Let's do actually negative 1/2 times negative 1/2 plus 2i, just to make it a little more exciting. All right. Don't be intimidated by the fraction. We're still going to use our distributive property of going first, outer, inner, last. I'm going to do negative 8 times negative 1/2 is positive 4, right? That's just asking what's half of 8. Negative times negative makes positive. Half of 8 is 4. Outer, negative 8 times 2i, minus 16i. Inner, 4i times negative 1/2. Positive times negative will be negative. And again, we're just asking what's half of 4i. That's going to be 2i. And then 4i times 2i is going to be plus 8. That's 4 times 2. I times I squared. We're going to see that I squared show up a whole bunch. That's why it's important to talk about that I squared before we get into this. Now, how do we deal with this? Well, we have this plus 8i squared, just like before. We know that I squared is negative 1, so this is the same as 8 times negative 1, or negative 8. In the next step, I'm also going to combine these like terms in the middle, so that gives us 4 minus 16i minus 2i minus 18i minus 8, right? 8 times negative 1 minus 8. Lastly, let's combine these like terms. 4 minus 8 is negative 4, and notice how I'm going to write my final answer in this a plus bi form. The real number first, the I second. Just like that. Alrighty. One more multiplication example, and then we'll move on to division. Something like this. Don't be intimidated by the radical. Ready? 3 plus the square root of 7i squared on the outside. Ooh. You might be like, but Mr. Giorgio, this doesn't look too much like a multiplication problem. It doesn't look like these where we have two binomials being multiplied together. But in fact, it is in disguise. What does it mean to square something? Well, to square something, we need to multiply it by itself, correct? So if I have 3 plus the square root of 7i all squared, what's really going on here is we're doing 3 plus the square root of 7i times itself, 3 plus the square root of 7i, right? So recognize that when we have this entire quantity that's being squared, I'm really multiplying this entire quantity by itself, all right? Because that's what it means to square something. If you did 2 squared, you would do 2 times 2. If you did 3 squared, you would do 3 times 3. If you do 3 plus rad 7i squared, you do 3 plus rad 7i times 3 plus rad 7i. And now we're just going to go to our good old friend, the distributive property, to deal with this. Hopefully that makes sense. Again, don't be intimidated by all the square roots and stuff. Notice what's going to happen. 3 times 3 is 9. 3 times the square root of 7i. Well, I can't really put a lot of that stuff together, so I'm just going to leave it as 3i square root of 7. Right? 3 can't really combine with anything. I can't really combine with anything. Square root of 7 can't really combine anything. They kind of just all hang out together. 3i rad 7. Okay? Notice the same exact thing is going to occur on the inside as well. 3 times I times the square root of 7 is exactly that. No like terms there, so we're just going to say 3I rad 7. And lastly, the square root of 7I times the square root of 7I. Well, the square root of 7 times the square root of 7 is going to be the square root of 49. And I times I will make I squared. So hopefully no questions as to how we got to this point. It's just multiplying first, outer, inner, last. Now, let's see how we can clean this up. This last term in particular is very, very interesting. The square root of 49 I squared. Well, the square root of 49 is just 7. And I squared is negative 1, as we saw up here. I'll even draw one more arrow going all the way down. Right? I squared is negative 1. Well, this really would just be the square root of 49, 7, times I squared, negative 1, or negative 7. Isn't that so satisfying when a big ugly mess like that turns into something super simple? All right, anyway, moving on. We got 9 plus. Let's put these two terms together. Notice we have like terms. I squared root of 7 here, I squared root of 7 here. 3 of them and 3 of them make 6I squared root of 7. And lastly, 9 minus 7 is 2 plus 6I rad 7. And notice that that is in our a plus bi form. All the real stuff is first. All the stuff with i's in it comes second. So we're done. All right. So hopefully adding, subtracting, multiplying, not too shabby. All right. Let's talk about dividing. A lot of people in the past, students, Algebra 2 students, generally seem to get kind of freaked out about dividing complex numbers. But dividing, just like it was when we were rationalizing, is really multiplying in disguise. All right? So check this out. Just as a little recap, right? So to recall. When I had a singular radical in the denominator that I was dividing by, all we did is we multiplied the numerator and denominator by that value, correct? So if I had something like 6 divided by the square root of 2, what I would do is I'd multiply the numerator and denominator by the square root of 2. And that is done to eliminate the radical component from the denominator, giving me 6 rad 2 over square root of 4. Well, the square root of 4 is 2, giving me 6 rad 2 over 2. And then I can reduce 6 divided by 2, which is 3 rad 2. Right? So nice little recap. The same exact thing applies with having singular complex or singular imaginary terms. Something like this. If I had 3 minus 2i, all divided by 4i. Well, how can I get that weirdness out of the denominator, that 4i? Well, what I can do, just like I did over there, it's a singular term. I'm going to multiply by 4i over 4i. Because what's going to happen when we do that, it's going to make this I squared in the denominator, and that's what's going to make those i's go away. You might have already kind of been like, oh yeah, I squared. That's how we can get rid of that, right? Notice what we get when we do that. I'm going to get in the denominator, 4i times 4i is 16i squared, or negative 16, because that's 16 times negative 1, which is I squared, right? In the numerator, we're going to distribute there and there. 4i times 3 is going to be 12i. 4i times negative 2i is minus 8i squared. Now, what's the deal with this minus 8i squared? Well, since I squared is negative 1, that's really negative 8 times negative 1, which is positive 8. So doesn't this become 12i plus 8? Kind of cool, right? Kind of cool. Now what I can do at this particular step is I can sort of split my fraction apart to say that I have 12i plus 8 all over negative 16, which would be the same as saying I have 12i over negative 16 and plus 8 over negative 16. And the reason that that's done is so that I can then write my final answer in this a plus bi form, which seems like not a big deal, but you're going to notice it is a big deal in the next example. Because if it's backwards, then that makes things difficult. Let's do the real part first. 8 divided by negative 16 is negative 1/2. That's how we can reduce that. And then over here, 12i divided by negative 16, we're going to say that that's negative, let's see, 12 over 16 we can reduce by a factor of 4. So that's going to be 3i over 4. And so that would be our final answer. All right. In fact, I know it may be intimidated a little bit by the decimals and such, but in the fractions, it's actually very rare to do one of these division problems and not get a fraction as an answer. So be prepared for fractions. Now, problems that I give you, I'm not going to give you ones that are crazy, insane fractions, but certainly halves, fourths, fifths, tenths. I think those are all certainly reasonable. All right. And you may see some other ones show up as well. But nothing, you're not going to get anything like the 200 something or other in the denominator. All right. You can get problems like that, but I won't do that to you. All right. So that's what happens when you're dividing by a single imaginary term. Just like with radicals, you multiply the top and bottom by that term. What if, though, we're dividing by an entire complex number? Consider an example like this. Negative 4 plus 5i, all divided by 2 minus 3i. Well, the concept in the issue is still the same, that I want to get that imaginary component, I want to get that I out of the denominator. But now we have to think about what would I actually multiply that by in order to make that happen. And what we would multiply it by is something that's called the complex conjugate. Just like conjugating a verb. All right? And the complex conjugate is, to define it for you, it's the expression that when multiplied to a complex value will eliminate any imaginary component. And the complex conjugate, the expression that when multiplied to a complex value will eliminate any imaginary component, the complex conjugate of 2 minus 3i is in fact 2 plus 3i. What gets changed in order to do the complex conjugate is the fact that we switch the sign of the I. And by switching the sign of the I, you're going to see that when we distribute, those i's will cancel out, and we'll be happy to go on our day. All right, so notice the complex conjugate of 2 minus 3i is 2 plus 3i. And vice versa as well. The complex conjugate of 2 plus 3i is 2 minus 3i. And this is why it's important to write things in a plus bi form, because if you don't, you may end up switching the sign of the wrong thing. If you switch the sign of the 2, that's not going to help you get anywhere. You'll still have i's in the denominator. It's important to always switch that sign of the I. And it's easiest when it comes second, because you just flip-flop that middle sign, right? Suppose I had 8 plus I, and I wanted to find the complex conjugate of that. Well, the complex conjugate of that would be 8 minus I. We just flip that I around. If I have, let's just do one more, square root of 2 minus 5i, the complex conjugate of that value would be the square root of 2 plus 5i. Notice the real part stays the same, but the sign of the I flips. All right. So returning back to our previous example, in order to do 4 plus 5i divided by 2 minus 3i, what I would do is I would multiply by the complex conjugate. Multiply both the top and the bottom by 2 plus 3i. And watch what we're going to get when that happens. In the denominator, let's do that first. I'm going to distribute. It's really two distribution problems, like two multiplications. Look, we're going to do 2 times 2, 4. 2 times 3i plus 6i. Negative 3i times 2 minus 6i. And this is good. This is what we want to see, this cancellation. Negative 3i times 3i minus 9i squared. Good stuff. We're going to continue with the denominator for now. I have 4 minus 6i plus 6i goes away. And minus 9i squared, well, I squared is negative 1. So negative 9 times negative 1 is going to become positive 9. 4 plus 9 is 13. Hopefully you see how that whole denominator works out to be 13. Let's talk about the numerator. Same thing, it's just a multiplication problem. Division is like multiplication disguised. Negative 4 times 2, negative 8, that's first. Negative 4 times 3i, minus 12i. 5i times 2, plus 10i. 5i times 3i, plus 15i squared. All right. Lastly, let's try and just simplify this as best we can. 15i squared is going to be negative 15. Everybody seems to be pretty comfortable with that at this point. Negative 8 minus 15 is negative 23. Notice I'm doing my real part first because I'm going to want that real part to be written first anyway. And then negative 12i plus 10i is minus 2i. And now the last thing I want to do is just split apart my fraction to write my final answer in that a plus bi form. I would split this apart to say that this is negative 23 over 13 minus 2i over 13. The reason why it's minus is because the second part is negative. You could certainly write plus negative 2i over 13. It's a little fancier to say this. And there we are. We can't reduce any of those, so we're done. If we could reduce one of them, then we would. If this was 26 over 13, that'd be great. We'd reduce it to negative 2, but not the case. All right? Cool. So hopefully that made sense. Nice little overview of dividing by complex numbers, as well as adding, subtracting, and multiplying. All right? If you notice, I spent a lot of time on multiplication because division is essentially just two multiplication problems. When I deal with a single imaginary term, multiply on the bottom, multiply on the top. Or when I deal with a full complex number, we use the complex conjugate on the bottom and on the top. So it really becomes, again, two multiplications. All right? I think we're going to call it for the day. I will do more examples if you'd like to see more examples. We have a lot of practice time in class, and that's a nice advantage of kind of giving you all the information now. I think that's the best way to go about it. I would recommend trying the practice problems on Google Classroom. I will post the answers so you can see the work done out for you, especially for the dividing ones. I think it's important for that. But in the meantime, I hope you have a great day, and thank you so much for your attention and focus. I'll see you soon.